Okay, happy Monday. Are we going? All right, we're on. We're live. Happy Monday. We're venturing into a brand new chapter 8 on chemical bonding. We're going to start talking about concepts of chemical bonds. So let's back up and let's look at why we are going into this, because this is starting chapters 8 and 9 to me, like I said on Friday, are really crucial for understanding of really life chemistry, the basis of biology. If you look at a molecule, let's just draw a couple of molecules up here for fun, just because, again, I want you to start to see organic molecules, because that's one of the main reasons why we're taking this class, is to be able to see organic molecules and to see what a chemical bond is. So this molecule here, okay, this molecule here is called morphine. Some people might know morphine. Heard of morphine. Okay, so that's morphine. Morphine is still number one molecule for pain. You can modify morphine by removing the hydrogen here. If I remove the hydrogen from morphine and I put a carbon here, it becomes codeine. So you just took down some of its activity. And some people ask me, well, then why is morphine, if it's number one, why is it bad? What's the answer? Why is morphine bad? It's very addictive. And so you might ask yourself the question, why is it so addictive? Well, here's why it's so addictive. You have a molecule in your body that looks like this. And it's probably one of the most powerful molecules in the body. And it looks like that. And it's called dopamine. Okay, so this is dopamine. Now, dopamine is the brain molecule. It's the molecule that says good, and it's the molecule that says bad. So when you think about vacation, you think about being in the Grand Canyon with your parents, your dad locked the keys in the car. You remember that. Why? Because it was a stressful moment, and there's a dopamine trigger released with that. You also remember the beautiful sunset. Why? Because there's a dopamine trigger with that. And the brain chemistry works this way. It's like a wheat field. The brain is like a wheat field. And the first time you go down that wheat field, you probably can't see it. Second time you go down that wheat field, you might be able to see it. The third time you go down that path, you're beginning to make what? You're beginning to make a road, a pathway through the wheat field. That's exactly the way the brain works. So that's why we have dopamine triggers, good and bad. All right? And that's why drugs affect this. So if you look at dopamine, this is good. If you look at, and we could also draw adrenaline. Adrenaline puts a bond there and a hydroxyl group here. That's adrenaline. So very similar. And adrenaline, of course, is the fight, flight, or freeze, also brain chemistry drug. So between dopamine and adrenaline, we have these triggers going off in our brain constantly. All right? Which is why, if you prefer methamphetamine, it looks like that. That's methamphetamine. Okay? So methamphetamine is a massively horrible drug in our society because it mimics the dopamine channel. It mimics the feeling of good. If I take this off of here and I put an acetyl group on it, and I take this off of here and I put an acetyl group on it, you just made heroin. And heroin is also one of the very, very powerful drugs that we have a huge problem. My wife, as an OB/GYN, she probably sees more heroin and meth because of her patient population. She's in high risk, so she deals with people that come in on some pretty bad stuff. And we just see that in our society, huge important. But here's the thing. Why is dopamine, or let's go back to morphine. Why is morphine so addictive? Now watch this. You might be going, why is he doing this talk with bonding? Because I'll tell you why. There's a chair right here. Do you see this? You see this group right here? It's called a benzene ring. It's actually called a phenol or a catechol. It's called a catechol. Watch this. This is morphine. Okay? Check this out. Watch what happens when I do this. What did I just do? What's it look a lot like? It's a lot like dopamine, doesn't it? So it competes for the pathway of dopamine as well as removing pain. And this is why that is so addictive. When you look at fentanyl, you might have heard of fentanyl before. Anybody heard of fentanyl? Fentanyl is also a molecule. It's kind of a cool molecule, a little bit different, but this is your introduction into the beauty of organic chemistry. Fentanyl also mimics, wait for it, there's fentanyl. Fentanyl is also a very important drug in our society. My wife just gave it to a patient a couple nights ago when she had massive headaches. It's very important, but it also can be very, very poorly abused, and it's a very, very deadly molecule. But here's the thing. Why is it that fentanyl looks like this, and before I erased it, morphine looks like this, and dopamine looks like this, and why is it that two carbons come together and form and put two electrons there? Carbon, carbon, two electrons, carbon. And you see how this, two electrons, carbon, what's going on with forming these bonds? So we left off talking about the fact that bonding is a continuum of electronegativity. And if I have two atoms that are of the same electronegativity, 2.5 and 2.5, carbon and carbon, then those electrons are shared equally between those two carbons. But if I have a carbon and a nitrogen, the nitrogen is going to keep those electrons a little bit more than the carbon, because that's 3.0 and that's 2.5. And when I have a double bond of a carbon and an oxygen, notice 3.5 and 2.5 causes those electrons to sit more on oxygen, causing there to be a partial negative here and a partial positive there. Meaning that my body, when it breaks this up, will send something in and destroy the molecule. That's how drugs are built or broken down in the body. And I know that from chemical bonding. And I know that from electronegativity. So the question then is, what's really going on between two carbons and two electrons? And how can I then predict that these structures are correct? That that's dopamine, or that's actually methamphetamine. They're a very easy molecule to make, by the way, just like on Breaking Bad. How is it that I can predict where those are and the chemistry of this molecule? How can I build this molecule? How can I make this molecule? Okay? And so you see that bonding is a massively important concept in all of, this is organic chemistry, but in all of chemistry. And the ability to predict where these electrons are is massively important, which comes from electronegativity, which we just came out of. So I think the power of this is just massively important for us to now go into what we're going to call the Lewis dot structures, the octet rule. Okay, all these kind of crunchy, stale things, but don't lose track of where we are. We're gonna land the plane and be able to start to use this in a powerful way to build molecules that change life. In fact, I don't know, I'll keep going all day on these. The one that changed the world forever is right here. Probably the most important drug ever to be. This one was actually discovered. I think this is fascinating because it was actually found on accident, and if it wouldn't have been. So this molecule here, anybody want to take a stab at the most important molecule ever be discovered? Anybody want to take a stab at it? Penicillin? Penicillin! Dong! This happens to be penicillin. This happens to be penicillin G. If you want penicillin V, you put an oxygen right there. Oh, that's kind of cool. That's penicillin V. And check this out. Just a little organic chemistry for you. If I put an amine group here, watch. If I put an amine group here on penicillin G, you no longer have penicillin G. You have ampicillin. Where it comes from, ampicillin. Amino is an amino group. And if you put a OH over here, you no longer have penicillin. You have amoxicillin. Okay? And so you see this whole family of these drugs are actually incredibly important. But once again, what's going on with the bonds? What's going on with 4 electrons in the oxygen and the carbon? What's going on with the carbon and the nitrogen up here? What's the nitrogen doing? It's a very important thing, all right? So that's why, to me, this chapters 8 and 9, or 7, 8, 9, electronegativity and bonding theories are massively important if we're going to understand really what's going on in the world of organic chemistry. Because the world of organic chemistry is not very complicated. It only deals with carbon, nitrogen, and oxygen. But there's so much going on with carbon, nitrogen, and oxygen. You notice all those molecules up there only have carbon, nitrogen, oxygen, and hydrogen. All right? So that's the world that we're heading into, which I think an introductory lecture or chapter like this is vitally important for our understanding of the bigger picture of, right there, snake, I'd be dead. A bigger picture of the world of bonding. So I know sometimes these chapters get a little bit dry with ionic size and electron affinity, and I get that. But remember why we're doing this. Remember the foundation that we are setting so that this chemistry makes sense. And then this chemistry makes sense, then biology makes sense. Because this is the foundation of things like microbiology, cell biology, all right? We're talking about the movement of carbon, nitrogen, and oxygen within the cells. So that's why, once again, I think that these chapters, 7, 8, 9, become really, really important in the grand scheme of your knowledge and setting that foundational knowledge. So we just came out of this idea of electronegativity. When you look at something like a molecule, here's water, right? Here's its dipole moment. And I begin to think, oh, okay, well, water has an oxygen at 3.5 and a hydrogen at 2.1. Therefore, my delta EM is 1.4. Oh, okay, that's a very polar bond. And so we say, and we use these little arrows with the plus sign to say there's a positive on the hydrogen, and the electrons are headed towards the oxygen, which is what that little arrow means. Here's my dipole moment. And if you remember, I talked about magnetic lava lamps, right? Magnetic blobs is how we should be thinking about these molecules kind of blooping around. There is an attraction between these polar groups. That's a polar nitrogen there. That's called a phenol right there. That's a polar oxygen, polar nitrogen, very polar sulfur group. That's an amide, actually a beta-lactam right there. Carboxylic acid, a very polar molecule, very polar part of that molecule. Why? Because of the electronegativity difference. That's how powerful electronegativity is. I can look at a molecule like amoxicillin up there, and I can say, oh, I begin to understand how it works and why it works within the body. In fact, the way this actually works is phenomenal. This beta-lactam right here, we'll call it an amide. This bond right here breaks. It's like spring-loaded, and it breaks, and it actually covalently bonds to the cell wall of the bacteria, and that's how it actually kills the bacteria. It's pretty fascinating how that actually works. But all of that to say, we're seeing now we can use this to predict polarity. We can use this to build molecules, which is what we really want to be able to do. We talked about bonding, but what really happens when 2 electrons do this? What's really going on there? Don't electrons really not like each other? I mean, the whole reason why I can't go through this desk right now with my hand is because the electrons don't like each other. The electrons of the desk don't like my electrons in my hand, therefore they stop each other. So why can't I go through it? Well, then why do electrons, if they don't like each other, why do they like each other up here in a bond? Well, that's a good, fair question. And the answer is, we don't know. They just happen to pair up. All right, Pauli exclusion principle. We proved it mathematically, therefore it is. Okay, so we see this idea of bonding here, and we want to take that concept now and begin to build molecules. And this is where we're headed. We probably won't build morphine, or we might build methamphetamine. It'd be kind of fun. But we're going to talk about this whole idea, this whole concept of bonding. Again, I will teach this chapter, next chapter, through the lens of electronegativity until hopefully you get tired of electronegativity. Okay? Because it is electronegativity that sets the foundation on which Dr. Nagalis will build for Organic 1 next year, and then I'll take that and build on Organic 2 the following spring. So it's super fun to see how this Pauling scale of electronegativity really does contribute so much to my understanding of these things that we call molecules. Okay, so we already went through all this. This is a review, very important. Blah blah blah. And there's where we left off. Talking about this concept, we had our 2 magic spots at 0.4 and 1.7, 1.8. Okay, we have polar covalent. We had non-polar covalent, we had purely covalent, and if you're above 1.8 and above, you're down here on your ionic. So again, we will build on this, and we begin to move into building molecules. And some of you that have had general chemistry before will know the term VSEPR. If you have not heard that term before, if you have not had chemistry, it's valence shell electron pair repulsion theory. So we're going to build on that. I think electronegativity and VSEPR theory are two of the more powerful theories for us to understand the world around us, and that's where we're headed. Okay, so we're going to build on this idea of polarity. All right, let's talk about Lewis structures. So we all have to do a couple things with Lewis structures. This is really fun. We all have to be able to count to 8, first and foremost. Pretty simple. We can all do that, right? We've been able to do that for a little while. So when I count to 8, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. Okay, there we go. That's it. You're good. You're now pros at Lewis dot structures. Those are the valence electrons. Now go back to what we know. We know that lithium has 3 electrons. So lithium is a 1s2, 2s1. So it only has 1 electron outside of the principal quantum level 1. Beryllium, 1s2, 2s2. Okay? So beryllium says I don't have a full 2, n equals 2, therefore I have 2 electrons that I can use. Boron of 5, 1s2, 2s2, 2p1. The 2p1, the 2s2, 3 electrons for bonding. Okay? My favorite, the greatest element of all time, 1s2, 2s2, 2p2. So it has a 2s2, 2p2, so it has 4 electrons. Wow, cool. Nitrogen, 1s2, 2s2, 2p3. So it has 2s2, 2p3, has 5 electrons. Where am I going? Oxygen, the antagonist of life. 1s2, 2s2, 2p4, 2s2, 2p4, makes 6. Right? 1s2, 2s2, 2p5 makes 7. 1s2, 2s2, 2p6 is full. Okay, it's 8 or 0. So that's where the 1, 2, 3, 4, 5, 6, 7 comes from. That's where we have to start. We have to start with our electron, and I don't think that's very difficult. But that's where we start with our electrons, what we call our valence electrons. Okay, and we're going to begin to build molecules using that. All right, so valence electrons, like I said, are those electrons that an atom uses for forming bonds. Okay? The electrons it uses to form bonds. So if you look at all these carbon molecules up here, if you go over here to penicillin, oh, this is amoxicillin. This is amoxicillin. If you look at this amoxicillin, all of the carbons here have 4 bonds. This carbon has 1, 2, 3, 4 bonds. This carbon has 4 bonds. There's actually a hydrogen right here, but we imply hydrogens in organic chemistry, so we don't always have to draw them in. So this carbon has 4 bonds. It has 1, 2, 3, 4. Huh. This carbon right here has 4 bonds. 1, 2, 3, 4. Huh. Carbon always has 4 bonds. And it's like the great Lego builder uses these little blocks, and the carbon is the 4 piece in the Lego kit. Always. One time it's been violated. Olaf won the 1994 Nobel Prize for making a 5-bonded carbon that only lasts for like 12 femtoseconds, so we don't have to worry about that. 4 bonds is carbon. Okay? Huh, that's interesting. Well, now watch. Watch the Lego kit. Here's a nitrogen. Nitrogen has 1, 2, 3 bonds. Nitrogen has 1, 2, 3 bonds. Nitrogen has 1, 2, 3 bonds. Oh, maybe nitrogen is the 3 piece in the kit. Okay? It's actually very important. It actually can be 4 pieces as well, but that's a salt. You don't free base. We'll get a free base in here. Okay, it has 3 bonds. Well, now look at oxygen. Oxygen has 1, 2 bonds. 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 Maybe oxygen is the 2-piece in the Lego kit of life. Pretty cool. And, well, let's just keep going. Maybe hydrogen is the 1-piece. Yeah, think of hydrogen as the electron. Put the cap on the pen. All right? Hydrogen, 1 bond. Hydrogen, 1 bond. Maybe hydrogen is the 1-piece in the Lego kit of life. Where does that come from? It comes from the fact that carbon's 1s2, 2s2, 2p2. Okay? It has the 2s2, 2p2. It has 4 electrons. It obeys the octet rule, so it wants to bring 4 more in. Right? Now that makes it pretty doggone cool, I think. So we're seeing that with these valence electrons, we're going to be building these really trick molecules. Okay? So let's look at something like carbon and see if we can come up with the structure for something like methanol. Okay, so methanol is H4O. Okay, CH4O. So let's see if we can draw a Lewis dot structure for this. So here's how we do it. Number 1, I have to decide how many electrons I'm talking about. Okay? So with this, I go to the periodic table and I say, how many electrons does carbon have in its valence shell? 1s2, 2s2, 2p2, so it has the 2p2 and the 2s2, so it has 4. Okay, I know that also says it right there at the 14, just take away the 1 and it's a 4. So carbon brings in 4 electrons. Okay? Well, how many does hydrogen bring in? Well, hydrogen sits over there in the 1, so it only has 1 valence electron. It's only an electron and a proton. It has no neutron, so it's just it only has 1. So this brings in 4 electrons. Well, that's kind of cool. I go back over to our window, the periodic table, and I look at oxygen, and oxygen is got a 6 above it. So it brings in 6 electrons. So total, I have to account for and figure out where I'm going to put 14 electrons. Okay? So I have 3 atoms. I have carbon, I have hydrogen, and I have oxygen. The rule says hydrogen will never be a central atom. Okay, it can't be, because it only makes 1 bond, so I don't worry about hydrogen. But between oxygen and carbon, how do I know which one of those is the quote-unquote central atom? That holds most times. A better rule is it's the least electronegative. Okay, yeah, and that's a better rule because that always holds. So it's the least electronegative is going to be your central atom, all right? Because everything on its periphery is really stealing its electrons. So that tells me then that carbon is probably bonded to oxygen, and so the structure then goes like this. Here's carbon, and it has its 4 electrons. Okay. And here's oxygen. It's oxygen, and it has its 6 electrons. Well, that's kind of cool. Okay. And now I've got 4 hydrogens to put around this thing. Well, like I said, hydrogen's an electron, okay? It's the cap, it's the pen cap. So, take a different color here. And so I'm going to take hydrogen, and I'm going to put one down here on oxygen, because it wants one. There we go. And I'm going to put one over here, because carbon says cool. And then put one over here, and carbon says cool. And put one over here, and carbon says really cool. So there you go. There is the Lewis dot structure for methanol. Okay? So methanol should have 14 electrons, and oxygen and carbon always obey the electron, or excuse me, the octet rule. So carbon says 2, 4, 6, 8, cool. Hydrogen always has 2, so it doesn't obey the octet rule. 2, 2, 2, and 2. Oxygen always obeys the octet rule, so it's 2, 4, 6, 8. It's happy. Hydrogen only wants 2, and it has its 2, so we have 2, 4, 6, 8, 10, 12, 14 electrons. Everything is accounted for. Okay? So that's a Lewis dot structure, all right, using the valence electrons. And they're fun to make. And so what we do in chemistry is we say 2 electrons is a line. So that becomes this. There you go. And there's the structure of methanol. Okay. Now, the reason why sometimes the line chemistry is a little bit misleading is because we don't think of these in terms of electronegativity. We should be. Remember, this is 2.5 and this is 2.1. Therefore, they're just a tiny bit closer to carbon than hydrogen, but not much. Still in the nonpolar region, 0.4 of a delta En. So this is 0.4 delta En. This is 0.4 delta En. This is 0.4 delta En. This is 2.5 and that's 3.5. So what about these electrons? What about the electrons right here? Well, they're at 1.0 delta En, therefore they're on oxygen. Okay? So that's why the line sometimes is a little bit more misleading. If we drew those, we'd be like, oh, okay, they're sitting more on oxygen than carbon. They're moving towards oxygen. Okay? So that's why we say, okay, well, that bond is actually a polar bond. And so we put that little dipole bond on there saying that those electrons are headed towards oxygen, causing carbon to be a little bit more positive and oxygen to be a little bit more negative. Okay? So again, that's why sometimes the line structures, we're really losing the fact that we're just talking about electrons here, and those electrons are may or may not be shared between those 2 atoms equally, and probably aren't unless they're the same atom. Make sense? And so that's why on some drawing like this over here on amoxicillin, I'm going to put my hydrogen in here. Okay. So you put something on like amoxicillin, you can now look at this and go, oh, well, there's 2 electrons between them. There's 4 electrons between. We'll talk about those later. There's 2 electrons between. What are those electrons doing? And that changes the overall profile of the molecule itself. All right, super cool stuff. So, number 1, we want to be able to count to 8 off the periodic table. All right, so that's where we start, counting to 8. The octet rule should be the octet obsession, and there it is. Okay, so that doesn't change as you go down a family. Still remains the same. So like our chalcogens right here are 666. Our halogens are 777. Our well, the next one over, nitrogen 555. Here's carbon, silicon, germanium 444. Boron, aluminum 333. Alkaline metals, alkali earth metals, and you can see how this all works. Okay, we good? This over here. Note, when you get down to xenon, it becomes 8, not 0, and I'll explain that when we get to some cool molecules with working with them. Okay, any questions on that? Okay, pretty straightforward? Okay, so let's say we did something like phosphorus trichloride. The first thing we want to do is we want to go to the trusty dusty periodic table and see how many electrons phosphorus has. So let's go with phosphorus. And when I look at phosphorus on the periodic table, I know that it has, because it sits right underneath nitrogen, I know that it has 5 valence electrons. So I put my 5 down. Trichloride, I have 3 chlorines. Chlorines are 7. So 3 times 7 is 21. So I have a total of 26 electrons. Okay? So then the question is, where do they go? Well, phosphorus and chlorine, phosphorus being less electronegative than chlorine, will be the central atom. So I'm going to put phosphorus in the middle. So it'll be phosphorus with its 5 electrons. 1, 2, 3, 4, and 5. Okay. Then I'm going to bring chlorine in and say chlorine has 7. So chlorine comes in with its 7. Chlorine comes in with its 7. And chlorine comes in with its 7. And looks pretty good to go. Now let's make sure that I have 26 electrons total, and everybody has 8. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons. Chlorine has 2, 4, 6, 8. Chlorine has 2, 4, 6, 8. Chlorine has 2, 4, 6, 8. Phosphorus has 2, 4, 6, 8. Good. Good to go. Okay? So that is what we call the structure of phosphorus trichloride. Now, we will abbreviate this way. We will say that really then, we mean that it looks like this. And oftentimes we don't put, so there's phosphorus. It has a lone pair of electrons that stays in what we call a non-bonding orbital. And it has, the other ones are all considered bonding. Okay, so this is bonding, this is bonding, this is bonding, those are non-bonding. All right, we good? Okay, sometimes we have some choices to make. So here's phosphorus trichloride, central atom again being the least electronegative. But here's the thing. Let's see if we can come up with a decent Lewis dot structure. It's kind of bad not having a clock back there. So I don't like looking at my watch. I'm not bored at all. It's just I want to stay on target. It's much easier to glance up there once in a while than do this. So it is missing though. So I am doing this today. Okay, so let's see if we can do carbon dioxide. Now this is important. So this is going to be a little bit weird. So if this is new to you, or if this is something that you struggled with the first time you had chemistry, stay with me, because this becomes foundational in understanding how it is I predict a better Lewis dot structure. And then we're going to get into resonance and some really fun patches on the theory, because the theory is incomplete. So carbon dioxide, I'm going to go to the periodic table, and I'm going to say I've got 4 electrons plus 2 times 6 for a total of, should be 16 electrons. Right? I did my math correctly. But here's the thing. Watch what happens. So carbon, the central atom, because it has a lower electronegativity than oxygen, has its electrons. And the big, mean antagonist oxygen comes in and says, well, I've got 6. And oxygen over here says, I've got 6. But here's the problem. I only have 16 electrons to work with. I'm done. Right? If you count them all, 2, 4, 6, 8, 10, 12, 14, 16. I've only got 16, but I don't have 8 around these things. So what do? I have 2 choices. One choice is to bring this electron and this electron into share, and bring this electron and this electron into share. So what that looks like then is this. Okay? So I still have 16. 2, 4, 6, 8, 10, 12, 14, 16. And now oxygen's happy. 2, 4, 6, 8. Carbon's not happy, but it has its 8. 2, 4, 6, 8. Okay? And oxygen has 2, 4, 6, 8. So one possibility is to draw carbon dioxide like this, to have what we call a double bond. But there's another way that I can bring these electrons together. If I do it this way, let's say oxygen, let's say oxygen grabs one of carbon's. So this oxygen here grabs that electron. This electron goes down, but then the oxygen shares a whole second pair. That's going to look like this. Where did I do it? That way. Okay. So that's another way that I could bring The question. No.
Yeah.
Yeah.
So are these simply just two different ways to write it, or are those
No.
two different ways that?
Yeah, two possibilities, and we have to be able to determine which one's correct, and I'll show you how we're going to do it. Cool. So watch. 2, 4, 6, 8, 10, 12, 14, 16. We only have 16, we're happy, okay? 8, 8, and 8, correct? Watch. 2, 4, 6, 8, 10, 12, 14, 16. Also 16. And we're 2, 4, 6, 8. Carbon's 2, 4, 6, 8. Oxygen's 2, 4, 6, 8. So those are both valid Lewis dot structures, but one of them's incorrect. How do I know? Well, here's how you know. You have to be able to calculate the formal charge for each atom. It's very simple. Formal charge equals valence electrons minus non-bonding electrons minus half bonding electrons. And you have to be able to do this, okay? You have to be able to do this. This is one of the really important things for evaluating a good Lewis dot structure. So let's do this. How many valence electrons does oxygen have? 6. Minus non-bonding electrons. So 6 minus non-bonding electrons. 1, 2, 3, 4. Minus half of bonding. How many are in the 2 bonds? 4. So half of 4 is 2. So that equals 0. So my formal charge on oxygen here is 0. Go to carbon. How many valence electrons does carbon have? 4. So this is oxygen. So carbon is going to be 4 minus, it doesn't have any non-bonding electrons. So it's going to be minus 0 minus half of bonding, which is half of 8 is 4, minus 4, which equals 0. So the formal charge on carbon is 0. And oxygen, again, here is the same as that one, but I'll do it just to show you, is 6 minus 4 minus 2, which equals 0. Well, that's kind of cool. All those atoms have a formal charge of 0. Let's go to the next one. How many valence electrons on oxygen? 6 minus how many non-bonding? 2 minus half of bonding, which is, what's half of 6? 3. Uh-oh. 6 minus 5 is, negative 1. So up here, positive 1, yeah, thank you. It's that new map. Okay, positive 1. Okay? Carbon is 4 minus, again, no non-bonding, and it has 8 bonding, so 4 equals, well, let's do, it has no bond, let's keep it 0 in there. 0 minus 4 equals 0. So carbon's still happy. Okay? And watch what happens with this oxygen. This oxygen is 6 minus 2, 4, 6 minus 1 equals negative 1. So this oxygen is negative 1. So the rule says the better Lewis dot structure is the one where the formal charges are 0. So that tells me that carbon dioxide looks more like this than like that. Because they're both valid Lewis dot structures. But the formal charges tell me that it looks more like that than that. And I know that because it's a nonpolar molecule. That thing over there is very polar. Yes?
So you ionize carbon dioxide.
Oh yeah. Oh yeah. So when you zap carbon dioxide, it's really some cool photochemistry here. those electrons are spin paired to Pauli exclusion principle. What you actually do is you put them into a higher excited state. That's called a singlet state. And it just comes back down. It comes off as phosphorescence. If you have an intersystem crossing, it comes off as fluorescence. It's actually super cool chemistry. So yeah, that's what's happening when you excite those electrons. And actually, you can actually find that form of carbon dioxide in the flight tube of a mass spec. So yeah, pretty cool. And that's big, really tons of energy in there. Okay? Questions on this? Your turn then.
Yay.
See one, do one, teach one. Okay? You tell me the correct structure for what is the structure for BF3, boron trifluoride? We're still on? Yeah, we're on. Okay, let's give it a shot. So, boron trifluoride. Boron brings how many to the party? Brings 3. And how many does fluorine bring? 7, so a total of 24 electrons, okay? So, I'm going to drop boron, give it its 3, okay? Then I'm going to bring fluorine in and give it its 7. And fluorine in, and it's 7. And fluorine in, and it's 7. So if I count them all up, that should be 8 times 3 is 24. Cool. But octet, 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 not an octet. What do? Well, try bringing a pair in. And so that would give you this here. That would give you boron, double bond to the fluorine, single bond to the fluorine, single bond to the fluorine, electrons. Okay? Now, is that correct? Well, we got some work to do. So, if you'll see this, 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Good. Okay. So 24, everyone has an octet. Question is boron trifluoride happy that way? Well, let's do some formal charges. So fluorine is going to be 7 minus 4 minus 2, which equals a positive 1. So fluorine has a positive 1 on it.
That's not.
That doesn't sound good. Well, what about boron? Boron is going to be 3 minus 0 minus 2, 4, 6, 8, 4, which equals a negative 1. Uh-oh. Boron, a negative 1. Fluorine, a positive 1? Fluorine's the most electronegative element on the periodic table. It doesn't want to be positive. What's going on? It's not a very good Lewis dot structure. Ah,
You tricks.
I tricked you. Watch what happens if I don't assume boron follows the octet rule. If I just do boron, fluorine, 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 again, 24 electrons. But watch what happens now when I do fluorine. Fluorine is going to be 7 minus, happy with my electrons there. Minus 6 minus 1 equals 0. That's good. Boron is 3 minus 2, 4, 6, 3 equals 0. Oh, that's good too. So that says 0, 0, 0, 0. Uh-oh. What just happened? We see our first violation of the octet rule. Okay? So, here's the rule. There are 4 atoms that never violate the octet rule, and that's all you get. Okay? So, you want to call the rule, go for it. I call it the octet exception. It is carbon, nitrogen, oxygen, and fluorine. So, check this out. You want to see something really fun? If you go to chlorine, or let's do sulfur. Let's do sulfur hexafluoride together, and watch what happens.
So what are the violations?
What's that?
Are there more than just one violation?
Say it one more time.
Is there more than one violation? Or is one of them where you?
No, those are your only 4. They don't violate it. Everyone else, they can be all over the place. Okay, watch this. How many does sulfur bring in? 6. 4 times 7. For a total of 34. Is it 34? Okay, unless I'm doing new math, I think. Okay. Okay. Sulfur's central, so watch what happens with sulfur. So here's sulfur 6. 1, 2, 3, 4, 5, 6. Uh-oh. What's fluorine going to do? Well, crud. Fluorine has to go here. And fluorine, uh-oh, well, crud. Where are we going to put those other 4 fluorines? Oh my word, where, uh-oh. I don't know what to do. I'm so confused. Okay, so let's put fluorine in. It's 7. Let's put fluorine in with its 7. Let's put fluorine in with its 7. And let's put fluorine in with its 7. And are we there? Well, yeah, we are. We are 8 times 4 is 32 plus 2 is 34. So, wow, this is kind of weird. Sulfur tetrafluoride looks like this. Well, that's not very cool, because sulfur has 10 electrons around it. Yeah, no problem. That's what it actually looks like. And we'll see in Vesper theory that that's a seesaw. Okay, so with that, build on this. Again, the octet, the next row down, chlorine violates it, sulfur violates it, phosphorus violates it. Silicone's it's pretty obedient to the octet rule, but we do see some violations of it as well. Okay, all right, I will see you on Wednesday.